So the chemistry of carbohydrates. Now, carbohydrates are the most abundant organic molecules in nature. And they are aldehydes of ketone. They are aldehydes or ketone derivatives of polyhydric alcohols. Therefore, they're referred to as hydrates of carbon. And they play important structural and metabolic roles. And as you will notice this morning, glucose is going to be the most important carbohydrate in terms of discussion. All right, so the classification can be based on the number of subunits, such as monosaccharides, disaccharides, oligosaccharides, and polysaccharides. Monosaccharides, they're considered the building blocks because they cannot be hydrolyzed into simpler carbohydrates. And they're considered the basic monomeric units of simple carbohydrates as well. Now, these monosaccharides can be subclassified into the number of carbon atoms and if they're either aldoses or ketoses. So here's the example of the subclassification. Now, if the sugar has three, let me use the if the sugar has 3, 4, 5, 6, 7, and so on, number of carbon atoms, and if they are either aldose or ketose. So for example, you have a 5 sugar aldose, call that a ribose, and a, let's say 6 sugar ketose is called fructose. All right. Now, the difference between aldose and ketose is that in the aldose, aldehyde is their most oxidized functional group. In the ketose, the keto group is their most oxidized functional group. And usually the ketoses will have the suffix -ulose. Usually, not all. There are exceptions to this. Now, if you will notice on the left, you have an aldehyde. The most oxidized functional group is the aldehyde. And on the left, it's the ketose. So 3 sugar, you have an aldotriose here. So this is an example of an aldotriose called glyceraldehyde. On the right side, it's a ketone. Therefore, a ketotriose, an example would be dihydroacetone. Okay, now physiologically important pentoses, these are found in Harper's. You can just read through them. So the name of the sugar, the source, and the role they play, the importance. Pentoses, so 5 carbons. These are the 6 carbon important sugars. Again, the sources, and then their importance. Just read that in Harper's. Now, most of you found trouble discussing derived monosaccharides because they may not be in Harper's. So here, just take note that examples of derived monosaccharides are deoxysugars, sugar phosphates, sugar acids, sugar alcohols, and of course, amino sugars, which you will also encounter in the succeeding units. So an example of a deoxysugar. So in deoxysugars, one hydroxyl group is replaced by hydrogen. As you can see here, the example is deoxyribose found in DNA. So here, the hydroxyl group of carbon 2 is now replaced with just hydrogen. Another example of deoxysugar would be your L-fucose, found in glycoproteins. We will discuss that in subsequent units. Okay, sugar phosphates, very common. You studied DNA already. So you will note that the sugar can be bound to phosphate in the backbone of the DNA molecule. We'll discuss more on that later. Okay, sugar acids. On the left, you have a 1, 2, 3, 4, 5, 6 carbon sugar. Look at the most oxidized functional group is an aldehyde. So this is glucose. The right side is the sugar acid. So what happens is that glucose will be oxidized this time into, so look at the most, the carbon farthest away from the carbonyl carbon. This will become carboxylic acid now this time. So the glucose will become glucuronic acid. So sugar acids, when transformed from glucose, you just add uronic acids. For example, glucose becomes glucuronic acid. Just add uronic acid. That's a simple way to remember. Okay, now sugar alcohols, these are polyhydric alcohols or polyols. Their aldehyde or ketone group is reduced to an alcohol group. So we'll see that later on in the illustration. And its uses, they're manufactured by the reduction of monosaccharides. It's used in diabetic or weight loss products. They're incompletely absorbed in small intestines, and they yield less energy compared to sugars. So they have little or no dental acidity, therefore there's less dental caries, but overconsumption leads to bloating, diarrhea, and what's this, flatulence. Okay, so in sugar alcohols, as opposed to sugar acids, the sugar this time is reduced. So that, remember I said overconsumption, you get bloating and diarrhea, etc. Because if you consume a lot of these sugar alcohols in the form of artificial sweeteners, you find them in sugar-free products. What happens is that you will have a high intraluminal osmolality this time, because remember, they can't be absorbed, right? So what happens if there's a high osmolality in your intestinal lumen? It draws the water out. Therefore, you have bloating and what's called an osmotic diarrhea. All right, so for sugar alcohols, these are just very common examples. You find erythritol and xylitol and these are the ones you find in the sweetened, artificially sweetened products. Don't have to really memorize those, not really so important. Okay, so the last batch of derived monosaccharides or derived carbohydrates is the amino sugars, also called hexosamines. So this time the hydroxyl group is replaced with an amine group. And they're found in components of glycoproteins, gangliosides, and glycosaminoglycans. Example of amino sugars are D-glucosamine found in hyaluronic acid, D-galactosamine found in chondroitin, D-manosamine, and also in certain antibiotics such as erythromycin. Okay, so we're done with the monosaccharide. This time disaccharides, we'll just whisk through this very quickly. So disaccharides are two monosaccharide residues linked by a glycosidic bond. Examples are maltose, sucrose, and lactose. So you'll see here, two glucose residues plus two glucose subunits can form maltose. Glucose plus fructose, just remove the water, forms sucrose, and this is the glycosidic bond or linkage. And here you'll find galactose and glucose forming lactose. The bond here is a beta 1,4 glycosidic bond. Physiologically important disaccharides are sucrose, lactose, maltose, isomaltose, lactulose, lactulose, that's usually used as a laxative here, osmotic laxative, and trehalose. Okay, now let's discuss oligosaccharides. Oligosaccharides contain about 3 to 10 monosaccharides, and most are not digested by human enzymes. Examples of compounds containing oligosaccharides are glycoproteins. Okay, so here you'll find a protein embedded in the lipid bilayer of the cellular membrane. You have an internal or intracellular domain, and then you'll have an extracellular outer domain. It's the outer domain of the protein bound which contains the glycoprotein. So if you see in schematic, you will have what I mentioned earlier, the hexosamine, the amino sugars, and your various sugar components or sugar moieties. In this case, it's mannose. All right, so we're done with that. Polysaccharides this time are condensation products of more than 10 monosaccharide units. So they serve as storage or structural functions. So you have homopolysaccharides composed of a single monosaccharide species such as starch, glycogen, and cellulose. So here you'll find two native starches in the form of amylose, which is linear, and amylopectin, which is highly branched. So this, I think, is found in Lippincott. So here you'll find amylopectin, which I mentioned earlier was a branching polysaccharide. And in the linear chain, you will find that it is bound by an alpha 1,4 type of bond. The branching point has an alpha 1,6 bond, very similar to glycogen. Now, amylopectin, you find that in plants. Glycogen, you find that in animal muscle. Now, cellulose, you find this also in plants, but the branch this time of the linear chain, because cellulose is linear, is a beta 1,4. So that's the main difference, just the type of bonds. Now, aside from homopolysaccharides, you also have heteropolysaccharides, wherein you find two or more different monosaccharide species. They are closely associated with lipids and proteins, and they are found in glycosaminoglycans, glycolipids, gamma globulins, plant gums such as pectin and lignins. Now, this is just a table in Harper's. You just have to be familiar, but don't have to really memorize all these very tedious components. Just be familiar with it. For example, the first three are glycosaminoglycans, which we will tackle later on in subsequent units. And going back to the first statement I mentioned in the first slide, I said that glucose was the most important carbohydrate, which we're going to discuss this morning. And glucose contains or has a D and L isomerism. Okay, so the D and L isomerism is determined by the orientation of the hydroxyl group around the carbon atom adjacent to the terminal alcohol. So this is the terminal alcohol, the terminal carbon, which is farthest away from this carbon here is called the anomeric carbon because it contains the carbonyl group. So the farthest away is this terminal carbon. The one just adjacent to it will determine whether it is a D-glucose if the hydroxyl group is oriented to the right, and if it's an L-glucose if the hydroxyl group is oriented to the left. And you also have mutarotation. I'm sorry, optical isomerism. So it's just schematic here. It's just about one paragraph in Harper's, but here this is just how it is illustrated. You have a light, you have a polarizing sort of lens, and this is a solution containing glucose. So the purpose of this polarizing lens is that so that the light doesn't scatter in many directions, just one simple direction. So if the solution turns the light to the right, then it's called dextrorotatory. If it's turned to the left, then it's levorotatory. Now, you will notice that in Harper's, dextrorotatory and levorotatory are designated respectively as a plus and minus. But don't be confused between D and L and whether it's dextrorotatory and levorotatory, because you can also have a dextrorotatory D And you can also have a levorotatory, sorry, you can have you can have both dextrorotatory DNL. You can have both levorotatory DNL as well. So you can have a D minus and L minus. You can have a D plus and an L plus. Okay, so much for that. Glucose also has aldose ketose isomerism. So in this case, you have the same chemical formula, C6H12O6, but different structural formula. So glucose contains the same number of carbon atoms as fructose. The only difference is in the bonds here. We all know that glucose is an aldehyde and fructose is a ketose. You also have pyranose and furanose isomerisms containing the same number of carbon atoms. So the illustration to the right, you'll have still the same 1, 2, 3, 4, 5, 6 carbons, but the ring it forms contains 6 components. And on the right, you have glucofuranose, wherein the ring contains only 5 components, one of which is oxygen, and the 2 carbon atoms are outside the ring. Now, epimers. Epimers of glucose are what is exemplified here. Now, these are isomers due to the variation in configuration of the hydrogen and the hydroxyl group, either in C2, C3, or C4. Example, in the middle is glucose. Now, you can say that galactose is a C4 epimer of glucose, whereas mannose is a C2 epimer of glucose. Alpha and beta anomers. These are just differences in how the hydroxyl group is oriented in the closed form or the closed, what do you call this? The ring or the chair conformation. So you will note that this is the open form or the straight chain form of glucose. Now, when it cyclizes, you will form a ring, or in this case, a chair conformation. The hydroxyl group can be oriented here equatorially, therefore designated as beta D-glucose, or axially, designated as alpha D-glucose. Mutarotation, don't be too overwhelmed by this. These are just alpha and beta anomers in solution in equilibrium. And just take note that it can be interconverted from a straight chain to either being beta glucopyranose or alpha glucopyranose. So just note that in equilibrium, in solution, glucose exists as an open form in very, very small amounts, less than 1%. But the most stable form, of course, is the ring form or the beta glucopyranose, which exists in 63% or little less than 2/3, and 37% as alpha, just a little over 1/3. So the most common in solution will be beta glucopyranose. Okay, glucose structural conformation. Open chair form is the Fischer projection here, on the right, the leftmost, and you'll have a cyclical or ring form, exemplified as either Haworth or chair conformation. Now, what happens here is that glucose from the open form will form a hemiacetal, thus producing a cyclical or ring form, either projected as Haworth or chair conformation. Now, these Haworth and chair conformation actually the same thing. It's just how it is written or drawn. Okay, so closed loop. Now, just to give you like a summary for the cyclic structures, because they account for most of the properties of glucose. Now, the chair conformation is the most preferred form or the most favored because it's the most thermodynamically stable, and the conformation is not uniplanar. So these are the various configurations, Fisher, Haworth, and chair. And alpha and beta in Fisher is designated as right and left. In the Haworth, alpha is down, beta is up. And the chair, alpha is axial and beta is equatorial. Okay, we already saw that earlier. Acetal and ketal formation, don't be too worried about this. You know, when glucose in open form cyclizes, then you'll form a hemiacetal. And usually you'll find ketals and hemiketals in disaccharides. Don't worry so much about that. Okay, glycoside formation or bond formation. Glycosidic bonds are covalent bonds which links carbohydrates with other carbohydrates or even non-carbohydrates. So if the other group is a non-carbohydrate, that other group is called an aglycone. So you will have O glycosides wherein the hydroxyl group of the aglycone is involved in the reaction or the link. So you always links with the anomeric carbon. So this is just an example of what's this? Methanol. Methanol linking to the anomeric carbon, and you'll find or form a glycosidic bond. In this case, it's an O glycosidic bond. You can also have N glycosidic bonds wherein amine of the aglycone is involved. A very good example is adenosine. You already studied this when you studied nucleosides. So the ribose here, 5-carbon sugar, is linked to adenine via an N glycosidic bond right here. So you have O glycosides, you have N glycosides. By the way, these are reactions involving carbohydrates. You can have ester formation. Now, here you will find this when we study glycoproteins. This is a very typical example. Now, UDP is a very good glucose donor. Now, in this reaction, glucuryl transferase is the enzyme. It releases or gives off the glucose to this structure. You will learn about this more when we study glycoproteins. But for now, just take note that as the glucose is donated and attached to the elongating glycoprotein, it forms an ester bond. You can also find ester bonds in your phosphodiester linkage in your DNA backbone. This is, okay. So you'll notice that phosphorylation is also a reaction involving glucose. Now, why is there a need for glucose to be phosphorylated? Now, okay, so why phosphorylation? Now, when you phosphorylate glucose, you help trap or you help retain the glucose intracellularly. Now, when the glucose is phosphorylated, you form this structure, glucose 6-phosphate, and the glucose 6-phosphate or your G6P cannot diffuse through the cell membrane via carrier proteins, unlike the free glucose. So what disease can be related to this? What is a very common or the most common GSD or glycogen storage disease? It's the von Gierke's disease. The enzyme deficiency here is glucose 6-phosphatase. So you will study this in further units ahead, but just take note as early as now that when you break down glycogen, ultimately you will need that enzyme glucose 6-phosphatase to produce or to remove the phosphate from the glucose so that it can be utilized. Okay, so without this enzyme, you'll have accumulation of this glucose 6-phosphate. And I'm sure you've read in Harper's already what the symptoms and the disease progression is for this von Gierke's disease. Okay, another reaction is oxidation of sugars. Oxidation of the terminal carbon at carbon 6, of course, produces a uronic acid. I already mentioned this earlier. Now, glucose, look at the terminal carbon. When the terminal carbon or the alkyl is converted into a carboxylic acid, you'll have a glucuronic acid. From glucose, you have glucuronic acid. Now, what if it was galactose? Galactose oxidized will become galacturonic acid. Just add uronic acid. Reduction of sugars. We already mentioned this a few slides back. The reduction of the carbonyl carbon or the aldehyde or ketone group produces a new alcohol group called polyols. An example of a polyol or sugar alcohol is sorbitol. We mentioned that already earlier. And you will deal with this polyol pathway in further chapters, but don't worry about this at the moment. So when you reduce glucose, you can form sorbitol. Reduction of fructose can yield sorbitol or mannitol, and reduction of galactose can yield galacticol. Reduction of sugars can also be found in deoxysugars. Reduction of the hydroxyl group produces deoxysugars. For example, ribose can be reduced to 2-deoxyribose, found in your DNA RNA. The oxygen on the anomeric carbon of the sugar is not attached to any other structure. So they're called reducing sugars. So reducing sugars can react with chemical reagents. In the lab, you can use Benedict's solution to reduce the reactive component. Examples of reducing sugars are glucose, galactose, lactose, and maltose for the disaccharides. Examples of non-reducing sugars are the disaccharides sucrose and trehalose. So I think that's a good last slide. We're able to finish in less than 30 minutes. So let's stop the sharing here. Now maybe we can use the last minute or two before I give the floor to Dr. Pepito. If you have any questions regarding carbohydrates, since your exam for this will be up next week. Anyone? Understood? Just read, just take note of the highlights in this correlate, especially the ones not found in Harper's. But the majority of the questions will be from this correlate and Harper's, no other source. So we take it easy for a minute, and in about less than a minute, 9 o'clock, Dr. Pepito will give her correlate.
Okay, sige. Can you hear me?